So today we're looking at section 10.2, which is about finding arc measures. So we need to start by defining what is an arc. An arc is basically based on an angle, and an arc is really just a part of the circumference of the circle. So for instance, if I'm looking at this picture right here, X is what I call my central angle. Notice that the vertex is at the center. And then where the central angle goes out, the intersection points on the circle are A and B. And so essentially what I'm doing is I'm creating a piece of the circumference, kind of like crust on a piece of pizza, a slice of pizza. And this guy right here is the arc. So if the arc is large enough, in other words, if the arc goes halfway around the circle, then the arc ends up being called a semicircle. So in this picture here, you can see that you've got a semicircle, which is an arc, right? It's a piece of the circumference, but it goes halfway around the circle. So if the central angle, in this case, our central angle is here, angle ACB. If this central angle is less than 180 degrees, so in other words, it's less than what we would say is half the circle, then the parts of the angle are going to be on the interior of the circle, right? So I can draw any dots inside, and those are all inside the circle. Then the kind of arc that gets created is known as a minor arc. So another way of thinking about a minor arc is that a minor arc is always smaller than a semicircle. If you're not on a minor arc, then of course you're going to be on a major arc. So like this is a major arc. And one thing you might notice about a major arc is that a major arc is more than a semicircle. And that's the primary distinction between a minor arc and a major arc. So when we name minor arcs, the only thing that we need to do to name them is look at the endpoints. So like in this example, it's easy to see why the minor arc is named AB. But we could call the major arc AB also, since those are the endpoints of the major arc. So the way that we rename major arcs so that they aren't confusing with minor arcs is we just include one point that's in between the endpoints. So in this case, since D is between A and B, we can call the major arc ADB. And that way we won't confuse it with the minor arc AB. So when we measure arcs, the primary way that we measure arcs is we use the measure of the central angle. So in this case, if we look at our example, arc AB, the central angle is here. The measure of the central angle is 50, and therefore the measure of the arc is 50. Okay, so essentially you're doing a minor arc is always going to be equal to its central angle. And we have to be really, really careful because there's lots of times when we see angles inside circles that make arcs, and this only works if they are central angles. In other words, remember that unless the vertex is at the center, this rule does not work, and we'll see that more later in the chapter. So let's take a look at this picture. It says find the measure of each arc. The good news about this picture is all of the angles are centered at C, the center of the circle. They all have their vertex there, so this should be pretty easy. So again, looking at the central angle, that means that AD is also 65 degrees. This right here, AB, is a diameter. And what that means is that this whole arc from here to here has to be half a circle. In other words, has to be 180. So if ADB is 65, then you can imagine what DCB has to be, and that would be 180 minus 65, so that would be 115. So that's going to give us the measure of arc DB. Then we can look at the other side of the circle, this side right here. This is obviously a semicircle. So this guy is obviously 180 degrees, or half of a circle, right? A circle is 360. So now I'm looking at finding the measure of arc ADB. So ADB is this guy, right? That's half a circle. So that's a 180. And then DBA is basically, let's take a look at it. We'll highlight it really quick. DBA is going to be from here all the way around. Keep going, keep going, keep going, keep going till I get to A. So DBA is the major arc, which is everything but AD. So DBA is essentially 360 minus 65, and that means that DBA is going to be 295 degrees. So if two arcs in the same circle are adjacent arcs, right? So that means that they have to have a common point, right? They intersect at one point. Then you should be able to add the measures of these two adjacent arcs. This is really similar to what we did when we were adding adjacent angles. So now this postulate says that the measure of an arc formed by two adjacent arcs is the sum of the measure of the two arcs. It's kind of wordy, but basically it's saying that you can add AB. So you can add this arc, and you can add it to this arc, BC, and what you get, the resulting arc, is from A all the way to C. So you can add two arcs together. So now we can add two arcs together in this picture. So let's take a look at it. First of all, we know that this guy, let's label some of the angles in here. This is going to be 90 degrees. And that means this has to be 90 degrees, right? Because PR is a diameter. So then SR is 35. And since I know that all of this has to equal 180, then this must be 145. Now, labeling your circles like this before you get started will make the work you do a lot easier. Because now we can just look at the diagram and we can start noticing things like, okay, SR is 35 degrees. And now SRQ is going to be 35 plus 90. So 125 degrees. And then PQ, that one was pretty easy. That one was 90. And SQP. So here we go. SQP is going to be this guy. And that guy is going to be 180 plus plus SR, which was 35. And we're going to get 215. You'll be practicing more of these tonight. So we can use our knowledge of arcs and central angles to find arc measures even from pie charts. So the example at right shows the results of a survey asking people how many minutes they spent brushing their teeth each morning. So if I want to find, let's see, arc ABC, ABC goes this way. ABC. Then that means that I'm going to be adding 120 to 82. So that would be 202 degrees. Okay, this time let's take a look at BD. So BD is here. BD is going to be 13 degrees plus 82 degrees. So that's going to be 95 degrees. Then we can take a look at what's next? Major arc ACB. ACB. And this one's actually easier to notice that it's everything but 120 degrees. So it might be easier to calculate it this way. 360 minus 120. So 240. And then the last one is major arc CBD. CBD. And this is another one where you'll notice that it's everything but the little yellow wedge there. So everything but 13 degrees. So again, it might be easier to calculate it as 360 minus 13 degrees, which would give me 347. Okay, so we're going to look at the congruent central angles theorem and see if we can determine whether or not two arcs will be congruent to each other. So first we need to talk about congruent circles. Congruent circles, two circles are congruent if and only if a rigid motion or composition of rigid motions maps one circle onto another. So think about having the same circle and basically you're either translating it, right? Those rigid motions we talked about, you're translating it or you're rotating it or you are reflecting it. Let's put that one over here. Or you are reflecting. But we would not be dilating. We wouldn't be changing the size of it. So this theorem says that in the same circle or congruent circles, two minor arcs, so like this guy right here, CB and DE, they are congruent if and only if, so it's a biconditional theorem, if and only if their corresponding central angles are congruent. So if and only if these two central angles are congruent. And that makes sense because we know that whatever the central angles are, that's the measure of the arc. So if they don't have the same central angles, how can the arcs have the same measures? So let's take a look at a couple of problems. Decide whether or not these arcs are congruent. So even though these have the same central angle, remember that the beginning of the theorem said that if the circles are congruent, then ... So because we have not met the premise in this problem, these two circles are not congruent, then HE cannot be congruent to GF. All right, let's take a look at part B. Could it be that these two arcs are congruent, PQ and SR? Well, we know that the central angle for PQ is 65. Let's solve for the central angle for arc SR. What do I know about all three of these angles? I know they add up to 180 degrees, and that should make it fairly easy for me to solve for the central angle SR. So I'm going to take 180 degrees, and I'm going to subtract 50, and I'm going to subtract 65. And I find that this angle right here is 65. So in the same circle, two minor arcs can be congruent if their central angles are congruent, and that makes this one a yes. Last problem. First thing I need to decide is, are the circles congruent? Is circle O congruent to circle P? If it's not, then I don't even need to keep going. But since they both have the same radius, right? This has a radius of 6. This has a radius of 6. Now I can look and see, do they have the same central angle? So they do have the same central angle, right? They both have a 90-degree angle. And therefore, JK should be congruent to MN. And this also is a 90-degree angle right there. So this one is also a yes. All right, last theorem and last example here. This is a theorem which says that all circles are similar. All circles are similar. So unlike triangles, where we had to prove similarity by angle, angle, or side, angle, side, all circles are similar. So we don't ever prove two circles are similar. So in example 5, it says the circles at right are similar. Find the similarity ratio. So remember, the similarity ratio is like the scale factor. So we'll assume that it goes this way, okay, from the little to the big. And that means that we're going to put the radius of the larger circle over the radius of the smaller circle. And that means that the scale factor is going to be 2. Says, find the ratio of the circle's area, and what do you notice? So again, let's take the area of the larger circle and put it over the area of the smaller circle. And the reason why I'm doing it like that is because that's the same way we set up the scale factor. We did the larger circle over the smaller circle. So now let's find the area of these circles. So quick refresher about finding the area of a circle. It's pi times the radius squared. Pi times the radius squared. Let's simplify this. We're going to get 16 pi over 4 pi. Should notice that the pi's cancel. And we can also simplify 16 over 4, and so we get 4 over 1. So what do we notice about the ratio of the areas in comparison to the scale factor? Well, what we should know is that the ratio of the area is equal to the square of the scale factor. And that's actually exactly what we found when we were looking at scale factor and area for triangles. So all we're really doing is confirming that when you have similar shapes, in order to find the ratio or the scale factor for the areas, it's just the square of the ratio or scale factor of one measurement, one linear measurement.